Welcome to the National University of Singapore, or in short, NUS. It is Singapore's flagship university, and we at Team Aero NUS hopes that through this video, you will understand what makes NUS a leading global university centered in Asia. This year, Aero NUS consists of 12 students across different academic years. Although the team is entirely student-led, we still receive guidances from our faculty advisor weekly for progress and design reviews. We are honored to be part of AIAA DBF 2021 alongside our brainchild, Aero J2. Despite the ongoing pandemic, our team has shown resilience and great team chemistry throughout the entire competition schedule. Without further ado, let us bring you through the phases of our life-changing experience. Hi, welcome back.
The Aero J2 has a wingspan of 4.92 feet and a length of 3.95 feet. The aircraft has a mid-wing design and employs a tail dragger configuration for its landing gear. The wing has an area of 4.84 square feet and utilizes a Clark-wide airfoil with a 5-degree dihedral. The wing is made of 3 16-inch basewood spars, 10mm foam ribs, 5mm foam skin, and a carbon tube joiner to attach it to the fuselage. The vertical stabilizer is 0.409 square foot and the horizontal stabilizer is 0.679 square foot. The vertical stabilizer has a 1/4 inch balsa wood frame and 5mm foam infields. The horizontal stabilizer utilizes the NECA 0010 airfoil and consists of a 1/8 inch balsa spar and 3mm foam skin. Here are the control architecture diagrams. The diagram on the left shows the control architecture of the Aero J2, while the diagram on the right illustrates the control architecture of the external sensor. A separate lithium polymer battery is used to power the LEDs of the external sensor.
This is the mechanism and payload to be installed in the aircraft.
The towed sensor is cylindrical in shape and contains 4 stabilizing fins on one end, as well as a tangent ogive nose cone on the other. On the sensor body, there are 3 pairs of LEDs which will flash in the preset pattern in fulfillment of the competition requirements. The deployment mechanism consists of 2 main sections, the deployment arms as well as the lower assembly.
The lower assembly consists of a frame, which includes a base, 2 side walls, as well as a curved front cover. The sensor housing helps to reduce the shaking of the sensor while it is fully retracted. The auxiliary spool exists to allow for minimal changes in the center of gravity of the plane by changing the direction of force of the sensor weight. A continuous motor servo as well as the main spool is located near the point where the deployment arms are attached to the spool assembly.
The upper assembly consists of a base for which the deployment arm servo is mounted on, as well as the deployment arms, which are fortified with triangular supports. The deployment arm servo is mounted on top of the base, with a 4mm piano wire acting as a servo linkage to connect the servo with the deployment arms.
The propulsion system is designed to meet the 840-watt power requirement of the aircraft. As such, the motor selected is the E-Flight Power 25BL Outrunner motor, which has a maximum input power of 850 watts, just above our power requirement. The motor is rated at 14.8 volts, and a 4S LiPo battery with 5000 mAh capacity is chosen to supplement it. Through our propulsion tests on many different propeller sizes, the propeller chosen is the 10x5 carbon propeller made by Aeronaut. This propeller is capable of producing sufficient thrust at a lower power rating and propeller weight.
The following are the mission requirements that we have gathered. The important points to highlight would be that the sensor and its mechanism has to be carried internally, while the deployment of it shouldn't shift the CG of the aircraft by too great a margin. Secondly, based on mission scoring, all 3 missions and the ground mission are weighted equally, hence carry the same priority. Based on sensitivity analysis, these are the 3 key requirements that we have come up with. From sensitivity analysis, we chose to focus on the overall mission score. Based on the analysis, we concluded that 3 factors were of utmost importance, that is, the number of containers, sensor length, and its weight. By plotting a 3-dimensional graph in Python and introducing a power limit, we concluded that a single large sensor is the most optimal for scoring. This conclusion was corroborated by an analysis on mission scoring. From the graph shown, the score achieved by having a single container is only surpassed when we exceeded 8 containers.
Thanks for the great informative presentation, guys. So next we have the demonstration, so stay tuned.
Still and silent, calm before the storm. Gold and diamond, jewels behind the throne. Into the night, out of the dark, take to the sky, chasing the stars. All that we said, all that we are, waiting to fly. This is the start.
What do you think?
Hide and seek, reason and
Shane, pass or fail?
rhyme.
This one.